Welcome back, everyone. In this lecture, we're going to be focusing on creating the LSTM model that will later generate characters for us. We're also going to make the model flexible to either use CPU or GPU, depending on your hardware. Let's get started. Okay, here I am back at the notebook. I'm going to begin by basically getting a cell here and beginning to create the class. So we're going to say class, and we'll call this our character model since we're going to be generating characters. And we inherit from nn.module, just as we have before. And this is going to look a little bit similar to our previous models with recurrent neural networks, but it's going to take some more information regarding the actual text itself. So in our instantiation method, we're going to pass in all characters, essentially a set of all the unique characters. We'll define the number of hidden layers we want. I'll go ahead and set the default to 256. Again, that's something you can play around with. We'll set number of layers equal to 4, another thing you can play around with. We're going to have a dropout layer, so we'll say that the dropout probability is equal to 0.5. And then finally, I'm going to have the model be flexible to either use GPU or not use GPU. Well, by default, we'll say not to use GPU, but basically, this is going to allow us to have if statements that will create tensors with either .CUDA at the end of them or not, depending on if use GPU tag has been set on or off. I'm going to zoom out one step out so we can see everything. So we have our instantiation method. First, we're going to set up all our attributes. So we'll say super underscore underscore init underscore underscore to instantiate the inherited module. And then I'm going to set a lot of these just as our attributes. So we have the dropout probability equal to the dropout probability provided by the user. We'll have self num layers equal to num layers. We'll say self num hidden equal to number hidden, how many neurons per layer, and then we say self.use GPU equal to, whoops, make sure that says use GPU equal to use GPU. Okay, so we have our attributes. Next, we're going to do here, yet still inside the instantiation method, we're going to set up our character set, our encoder and decoder. So we'll say self.all characters is equal to that set of all characters that was passed in. And then from this, we can create an internal decoder and encoder that the model will have. That way, this model is flexible to any text data set. So we'll say dictionary, enumerate, just as we did before, all the characters, that's our decoder. And then we're going to have our self encoder, which just as before is going to be character and index, key value pair for the index and character created in decoder items. So there's our built-in decoder and encoder that come with the model. Next, it's time to actually start defining some of these layers. So we'll say self.lstm is equal to nn.lstm, and this is going to be the length of all characters. So we can say self.all characters by the number hidden by the number of layers, the dropout probability, or dropout is equal to drop probability, and then we're also going to say batch underscore first is equal to true. So let's take a look at this, make sure we understand it. If we take a look at LSTM, recall that it has several parameters being passed in, but essentially we have the input, which is of the shape, sequence length, batch, and input size. And then we're going to have, remember, we have our hidden state and cell state coming out as well. If we take a look at the actual batch first parameter, so here we have batch first. So if this is true, which is what we're stating, then the input and output tensors are provided in this format, batch, sequence, feature, which is the same format we're going to be using that we're going to use based off our batch generator object. So that's why we have it that way. And then recall these first parameters are the input size, the number of expected features in the input X, and now it's basically one feature per character or per unique character. Then the hidden size is number hidden that provided, and then number of layers. Okay, so we have self LSTM, where essentially recall that these number of the input size is the number of expected features. So essentially each character is its own feature that will have its own probability at the end. Then we're going to have self dropout be equal to a dropout layer. So we'll say dropout, pass in the drop probability, and then we'll have a last fully connected layer. So fully connected linear is equal to nn.linear number hidden by the length of self dot all characters. So we have that ready to go. Up next is to define our forward method. So we'll say df forward, take in self x hidden. And it's essentially going to look really similar to what we've done before. We have the LSTM output as well as our hidden output equal to self LSTM, pass in x and hidden. Then after that, we're pass that into the dropout layer. So we say drop output is equal to self dot dropout, and then we're going to pass in the LSTM output. And then we're going to say drop output again is equal to, and here we're going to do a little bit of reshaping so that we can connect this to our final linear output layer. And the way we're going to do that is by saying drop output and then call contiguous and then say view this as -1 by self dot number hidden. And that reshapes it so that we can connect it or pass it into our final output layer. So we say final out is equal to self dot fully connected linear drop output. And then we're going to return our final output along with the hidden state. And we're going to have a method here called hidden state. And the reason this is now a separate method is so that we can be flexible depending on whether or not we're using GPU. So the hidden state here is going to check if we have a CPU. So if we decided to actually use the GPU, then, and this should look pretty familiar to us, we'll say hidden is equal to torch.zeros by self dot number of layers by batch size by self dot number hidden. And then what we're going to do is at the end of all this, we're going to call CUDA on that. And remember, this is essentially a tuple for both the hidden state and the cell state. So I'm going to copy this, put a comma after it, and then also paste it here, close off that tuple. So I'm adding the CUDA if I happen to decide that I want to use the GPU. If that's not true, then we're going to say else, and we're essentially going to copy this and then remove the CUDA call. So we'll copy this, go ahead and paste it in, make sure our indentation is correct, and then remove these .CUDA calls if we're not using GPU. And we still have it as a tuple. And then after this, we can return hidden. Go ahead and run this, make sure we didn't commit any typos. There's a lot of code here and a lot of opportunity to commit typos, so I would highly suggest that if for some reason you're getting an error further along this notebook, that you just copy and paste our code, or preferably just run our notebook directly. Okay, so let's go ahead and create an instance of this model. We'll say model is equal to character model, and then we just pass in what all the characters are. Remember, all characters, we already defined that as a set earlier, literally called all characters. Then we have the number of hidden layers. We can define this as something like 512. It's up to you, you can play around with these. Number of layers, this is going to be 4, it's going to be 3, etc. The more hidden units and the higher number of layers, the longer the training time is going to take. Dropout probability, I would highly suggest that you start off with a 50% dropout probability. That's typically a good choice. And then for my particular case, I'll say use GPU equal to true. So we'll go ahead and run this. And if we want to figure out how many parameters there are, we can say total params is equal to this empty list, and then say for p in model.parameters, go ahead and say total param and append the integer of p number of elements. So run that, and you can see the list of the total parameters. You can see this is a pretty large network. So if we sum this up, we're dealing with about maybe 5.5 million parameters. So a good rule of thumb here is that this total number of parameters is roughly equal to the size of your data set. And if you recall, the size of our data set is roughly 5.5 million. So that's a good way to adjust the number of hidden units as well as the number of hidden layers. So you can play around with that depending on how large your text data is, because you want to prevent overfitting by having too many parameters for too small of a text data. And you also want to prevent underfitting by not having enough parameters for a large enough data set. So the total parameters should roughly be at least the same order of magnitude as the length of text. Okay, so now let's go ahead and define the optimizer and loss. We'll say optimizer is equal to torch.optimatom. Model.parameters. We'll go ahead and set a learning rate of 0.001. And the criterion here, because this is technically more categorical, we'll say it's a cross entropy loss. And then finally, what we're going to do here is set up our training data and validation data. We'll go ahead and set aside a piece of data for training, and we can do this based off our percentage. So you can say training percent, and for example, let's say we wanted to use the majority of the data as training because we have a really large data set. So we'll say 0.9 or 90% of our data will be training. If we check the length of our actual encoded text, then that's about 5.5 million, maybe 5.4 million, which means if I multiply this by the training percent, I get some sort of number, but I want to use this as an index position to cut it off. So we'll round that using an integer, and then that will allow us to basically say our training index around the 90% mark will be there. So that now our training data is equal to the encoded text starting from the beginning, go all the way to that training index, and then our validation data or test data, we'll say encoded text, and then go from that training index all the way to the end. Okay, coming up next, we're going to focus on training the network. That means setting up the variables such as epochs and batch sizes, and then actually setting up our epoch training loop. Thanks, and I'll see you there.